In this video, we're going to start talking about diagnostics and remedial measures. That is, we want to, anytime we get ready to do regression, we have to make sure that our necessary assumptions are satisfied for actually building a regression model, namely these. So we want to be able to somehow check or test for those assumptions, and also what can we do if those assumptions aren't satisfied. So sometimes this is called diagnostics and remedial measures, or we'll call it maybe evaluating and adjusting for model assumptions. So the assumptions in section 2.4 of your notes there can be summarized like this. I stole this acronym from someplace online, by the way. This is not my idea, but it's pretty great. LINE. L for the conditional mean response, expected value of the response, given some x variable value, is a linear function of the predictor variable. That's assumption number one. Also, I stands for independent. The errors, these random error terms, these epsilons, are independent random variables, and the errors are conditionally normal random variables given the predictor variable values. And finally, the errors, these epsilon i's, have equal variance. Okay, so let's see what the idea is here. Is if you have you know, so if those assumptions are truly satisfied, you might have this kind of a picture. Can you see how I'm trying to indicate that there's a sort of a downward trend, right? Looks like that first of all, that the mean response, if here's my x-axis, the mean response, if I fix the mean response, then the expected value of the I'm sorry, if I fix the x variable, the explanatory variable, then the mean response is appears to be a linear function of the x variable there. The errors, these epsilon i's, should be independent. Okay, we can check for independence or autocorrelation, things like that. The errors, these epsilon i's, are conditionally normal random variables. That is, you should see them clustering pretty tightly around here, and then maybe sort of some spread outness like this. Sometimes we draw these density curves like so. Okay, but the idea is that no matter where you place the x, where you look along the x-axis, the y value should be behaving like normal random variables, and finally that they should have the same spread outness. Okay, the variance off of this line, or the standard deviations off this line, should be the same. It doesn't have to be a downward trend, of course. You might see something more like this, right? And of course, I'm assuming that the x values are, maybe in this case, I'm sort of thinking like, well, you fix the x values and you're going to make response readings at just those x values, but you don't have to think in those terms. It could be that you have, the idea is, sort of like this. Right. So you see a large clustering right in and around the line there, with a few values off the line, but that wherever you look, the errors have equal variance, and they're normal, and they're independent. The mean response rides along the line. Now here are a few pictures that might indicate how these model assumptions might not be met. How about for the line? For the L assumption, for the linear assumption. Okay, you might have a nice point pattern to the data, but maybe they're not linear. Okay, Okay, something like that. In this case, maybe more of a polynomial model might be better. And we will certainly talk about polynomial models. So the line assumption is not satisfied. What about if the errors are not independent? Okay. So if the errors are not independent, you might still see a nice pattern like this. It's going to be a little more difficult to check. You could still see a straight line kind of pattern like this. However, and so maybe this is your predictor variable, and this is your response. Okay, your predictor or independent or explanatory variable down here. Here's your response variable. However, maybe there's some hidden variable in here. Maybe there's another variable like time. Okay, so this is still part of this example. What if instead I tracked the response or looked at the residuals? Maybe residuals are the errors off of the regression line. If I looked at the residuals, here's 0, and just looked at these distances off the line, positive and negative, it might be that you see some kind of a pattern like this, in which case they certainly don't look independent, do they? Okay, so we can do something called an autocorrelation test to try to detect for those kinds of scenarios. Third, the normal assumption. Okay, what if it may very well be that the line assumption or that the linear assumption on the conditional expected response is still met, but that maybe the errors are no longer normal. Maybe they tend to be sort of right skewed. If this direction is positive, then we think of it could be that you have some kind of dispersion like that. You have a nice clustering in and around here, but so it could be that you have something like this, so that the error terms are not normally distributed. What do you do in those cases? I don't know. Maybe you could transform the data somehow using a function. And we'll talk about that later on. So again, maybe these are not normally distributed. And finally, okay, so I guess in this case the I assumption is not met. In this case, the normal assumption is not met. And then finally, what about the error terms having equal variance? So what if you have a case like this? Okay. It looks like the variance is increasing as the predictor variable is increasing, right? I mean, maybe there's a straight line model going this way, but these have a nice clustering over here, but the response is sort of getting very, very unpredictable as x increases. So you have this sort of fanning out of the data, and that's no good. Maybe it turns out sometimes you can apply transformations to the data sets and to sort of remedy that as well.